wanted to say, great job compiling your own methods and the mathematical concepts of such great figures as Pythagoras, Eudoxus of Cnidus, and Theaetetus into a coherent framework in the form of your Elements series. I mean, you're pretty amazing, my dude. Heck, the parallel postulate was your doing. Unfortunately, your great postulates and theorems fall flat in some pretty big ways. Oh god, I hate myself. Okay, let's go. Today I'm going to be explaining why 5 Euclidean ideas are not necessarily true on all planes. So to demonstrate, I'm going to be using these geometric solids that I made myself out of clay. I have a cone, a cylinder, and a sphere. For my line, I'm going to use these fun wrapping paper strips with a straight line drawn on the back. Number 1, a line may never intersect itself. Now, on a cylinder, if we wrap a straight line straight around it, heading due east or due west, it forms a circle. And a circle is a line that intersects itself infinitely. So it's still a straight line, as you can see when we unwrap it. It just intersects itself. Then we have our cone, and if you try to make a line around that that's a circle, it doesn't work, like it doesn't lay flat against the cone's surface. But if you wrap it like a ribbon where it intersects itself at one point, then it does work. And it is still that same straight line. 2, on any given surface, all lines look the same extrinsically. So extrinsically just basically means from an outside perspective, like as I am looking at this geometric solid right now. It's a cone, run a line over the top point of it, and it's not going to look the same as a ribbon-shaped line wrapped around it. On a cylinder, circle line is not going to look like either of those lines. Given a line and a point not on that line, there's exactly one non-intersecting line passing through that point. Now this is basically the parallel postulate, which is one of Euclid's big ideas, as I said in the intro. And on this cylinder, I have a line and then also a point not on that line. And on the cylinder, the parallel postulate is true. There is only one non-intersecting line that we can make to the existing line that goes through that point. As you can see, if we try to make a spiral through it, it's still going to intersect the existing line, so it's not going to work. There's only one line that we can do on a cylinder. On the other hand, we have this sphere, and if you take polar points on a sphere, every line on that sphere is going to go through those polar points, and every line on the sphere is going to be a circle. If the sphere has like infinite polar points all over it, then every line has to go through a pair of polar points, and every line has to be a circle, and they all have to intersect each other. So you cannot make parallel lines on a sphere. It's impossible. Let's try it with another point just to prove my point further. Ha, another pun. I'm sorry. I'm so sorry I'm subjecting you to this. As you can see, it intersects again, and there's just no way we can make a parallel line here. I think I'll name him Timothy. Number 4, 2 points determine a unique line. So on Timothy, our sphere, we can make a line that covers up both of his eyes that goes through both of those points. That is the only line we are going to be able to make that passes through both of those points. There's never going to be another one. We can try all we want, but it's always only going to cover one eye and not the other. It's never going to encompass both points unless it's that specific line. However, on a cone, if we take a pair of points that are polar, they're on exactly opposite sides of the cone, draw them with our fun little purple Sharpie. Looks kind of like a shark. And we run a line over the top of the cone going through both of those points. That is one line we can make. Obviously, it's a straight line, and it passes through both of the points. We can also make one of those ribbon-shaped lines that we saw earlier that passes through both of those points. Still a straight line, and it's different. So that's the key here. two different lines can be made. Who knows what else can happen? I actually have an additional example for this one. We have a cylinder. Here I'm just drawing a little dot on it and another one. We can make a line passing through both of these points. It's a circle around the cylinder. Cover his eyes up like in Bird Box. And we can try to make a spiral or a vertical line, but again, it's only going to pass through one of the points and never both of them, unless it's that specific line. Let's try it with another line. Cross out that old point and make a new one. We can make a spiral through these, but we can never make a perfectly vertical or horizontal line that will go through both of them, and we can never make another line that will go through both of them. Number 5, all straight angles are congruent. Now this one's kind of a doozy, but what I think is that we have this straight line on a cylinder. It's vertical. It's 180 degrees. Now, we also have this line on a cone going through the polar points and over the top. Now, there's got to be an angle on this line that is not 180 degrees because, well, it's a straight line. It has that bend in it. And there just have to be angles on it that are less than 180 degrees for that to occur. Oh, and here's a cool real-world application for non-Euclidean geometry. NASA will be using non-Euclidean geometry for rockets and space exploration, as rockets are basically just cylinders with cones on top, and space-time is curved around every object with mass, including planets, many of which are practically spheres themselves. Geometry is everywhere out there, and the exquisite geometry we find in nature is often non-Euclidean. Sorry, not sorry. Bye, guys.